So I wanted to share with everyone some work on like common sense and logical reasoning. And this is mostly our probing into the limitations of current natural language processing technology. So I organized my talk into 4 sections. So first of all, I'll give a brief review of where we are now. And then I briefly talk about the driving forces, but I believe everyone's familiar with that. And then I'll mention a little bit about what we feel are the directions of the bottlenecks. And then I'll present 4 probing work and basically 4 data sets on common sense and logical reasoning aspects. So first of all, very briefly, we've all seen great advance in natural language processing in recent years. And some of the applications are already helping us, such as chit chat robots. We can ask about the result of games, and we can shop online using these chatbots. Last year, there was a breakout of COVID-19, which still affects our lives. And some companies, they use machine translation to quickly translate some handbooks on how to prevent the spread. Of course, there are also machine translation systems that allows us to quickly understand like the situation in different countries. And something that people always boast about in natural language processing is probably should include these machine reading comprehension tasks where, for example, a machine can quickly understand the description of a film and then tell the reader like who are the stars and who is the director, etc. So, so here's a final example where news websites and other places like financial websites, they use automatic summarization systems to provide overviews of the contents. So as we probably all know that the driving forces are a deep learning and pre-training. So if I were to summarize it, basically I say, I first ask a large neural network to do sentence completion, a close test, or sentence reciting tests. So basically I ask the huge network to remember how to complete a sentence, regardless of whether we mask a word in the middle or we just ask it to start from left to right, complete a sentence or distorted sentence. So in this way, we collect a lot of intuitive information or superficial patterns from large raw data, which helps us to do a next step of fine tuning, which is when we're given a benchmark data, we split the data into a training set and a test set, and we try to guarantee that the training set and test set follow the same distribution. And then we fine tune the pre-trained model on the training set, and then we report the performance on the test set. As a result, we can see a lot of great numbers in a huge benchmarks such as glue and superglue. So for some of the tasks, we already reach or even surpass human performance. But this can give us give outsiders a feeling that natural language processing has advanced so much that we can start doing a lot of applications. But unfortunately, we find that the situation is not the case because our systems are not stable at all. So you can see a lot of examples where people work on and people analyze. In dialogue, for example, there is the user basically wanted to buy 4 bananas, but the user said 4 apples in the beginning and then changed their mind. But the dialogue system couldn't understand the user. One thing that we realize is shown on the top right. So when we come to numbers, especially those numbers that need a little bit of calculation, the system often make mistakes. So in the bottom, I see I show a gender bias issue, which is quite well known. So when you have a morphological language and you try to translate an English sentence into that language, sometimes the statistical bias in the data are reflected, which mess up the output. And here is an example in abstractive summarization, which I find also very typical. So basically, in the original passage, there was a 12%, like in line 6. So 12% of people claim that they wash their cars regularly, but it turns out that in the summary, the fact was completely distorted. And people say only 12% of the people surveyed asked their children to wash their cars. So this is an issue of faithfulness in abstractive summarization, but this occurs a lot in automatic generation tasks. So what are the reasons behind? So we did a lot of work, and a lot of researchers thought from different perspectives, such as there are people who study robustness, some people who study a counterfeit attack, etc., like contrastive examples. So I wanted to share with you some work that I believe related to cognition, but maybe it's only remotely related to cognition. So in the first example, I just wanted to probe whether the pre-trained models, this training scheme, can endow a model with common sense knowledge in a very broad sense. So we just arbitrarily ask common sense questions to test whether a model is capable to distinguish things that make sense and things that don't make common sense. And then we also did some a common sense study in the context of a dialogue system, and we mostly studied social common sense. And finally, I present two data sets, one on natural language inference and one on reading comprehension, about logical reasoning. And this is a long-rooted, deep-rooted task in language understanding. But it's only recently that people began to pick it up again. So let's start with a general common sense. I give you a very simple example. So for example, when I say, I put the elephant into the fridge, you find that this sentence is weird because the elephant is larger than the fridge. You can't put it in. But if I say I put the turkey into the fridge, you don't raise the doubt. So I think this is a common sense about size. So basically, we wanted to make such a data set that asks the model to differentiate two cases. Which one makes more sense? And then we ask the model to explain what's the reason behind that you believe that the other doesn't make sense. Where you can put a turkey into the fridge, but you can't put the elephant into the fridge. So this is the first task that we try. The second task is more difficult choices. So there are like misleading choices. For example, the color is the color the underlying reason, or is it because something cannot eat the fridge? We give this example is because our fridge is normally related with food. And the third task is even more challenging. So we ask the model to directly generate the reason. And then we try to do human evaluation or on whether the reason is correct. So another example is like this. Someone got an F in the exam, so he got disappointed, but he would be happy if he got an A in the exam. So we collected a data set of 10,000 such examples by crowdsourcing, and we try to evaluate how models perform. So we evaluate the models both by using it off the shelf or using the training set of our data set to fine tune it. So the table on the top shows that if you don't if you don't fine tune the pre-trained model, then they perform not so well. So for human participants, particularly there are students in my group, they can do very well. So when they do the binary comparison test, they can reach over 99% accuracy, because this is very intuitive. And I asked the student why they made the few mistakes. They realized they didn't carefully read the sentences, not because common sense is an issue. But for like pre-trained language models, they only reach 70% in a 2 tries classification test. And for 3 tries, the situation is worse. But if you look at the bottom left, so after I fine-tune the model with training data, the performance goes up sharply. They can reach over 90 in 2-way classification, also over 90 in 3-way classification in the recent choices. The situation is not so obvious when you look at the bottom right. So when we ask the model to generate the reason, actually the performance is not so close to human performance, even after fine-tuning. So when evaluated on both blue and human evaluation, the conclusions are similar. So I think this is very typical. It represents our a common framework in natural language processing tests. So for every task, for every benchmark, we train and we obtain good performance. Is that because we really, our model really understands the data? So some preliminary analysis showed there are actually spurious patterns. I'm not sure whether they are spurious, but there are definitely superficial patterns that allows a model to make use of the patterns to get the correct result. And we found some of these reasons, including the length, the number of words in different choices, and some superficial patterns like signal words, negation words, etc. And the overlap between the training and test sentences, and also the overlap between the question and the correct answer. So this might partly explain why a pre-trained language model.
Can I ask you a question?
Yes.
Okay, so you collect that data set that you said, that common sense reasoning thing there, and do you know how many common sense, how many are uncommon, sort of
how many are uncommon?
Unexpected?
Right. So when we design the data set, we set out 7, I believe it's 7 rules for the crowdsourced workers, and we have a second round of double check, and we try our best to make sure that these are all common sense, like everyone should know. It's unlike some of the common sense data sets that prior to our work, some of them actually ask about some knowledge where only a small number of people know, or so for example, the physical world knowledge, like speed and the acceleration, etc. But for this data set, it's more obvious common sense, such as can you walk to the moon, or can you walk to your school, or this kind of common sense.
Okay. So these sentences are provided by you. You just ask the annotator to annotate it. This is a common sense or not common sense, or is just garbage?
It's provided, the sentences are actually came from the annotators as well. We provided some examples, and people try to brainstorm such common senses. Actually, it turns out that they are not so difficult to think about. You just think about everyday life, and there are a lot of such cases.
Understand. So they wrote this.
They wrote this. Yes, they wrote this.
They wrote the sentences.
Yeah.
Okay. Okay, I understand. All right. Thanks.
Okay.
Thank you, Professor Bing Liu. Yeah, Professor
And
Bing
also
Liu
one more question. What is the training data?
Yeah. Sorry.
What is the training data?
The training data are also like annotated in the same way. So we just split the data set into several instances for training and several instances for development and final testing.
Ping, what did you say just now?
Oh, just try to tell everyone that you're from University of Illinois, Chicago. Yeah. Yeah.
Okay. Okay.
Welcome.
I have one more question.
Right.
So what happens? There are some common sense which is in the training data, but there's no correspondence. For example, I walk to the moon, that's in the training data, but in my sort of test data, I run to the moon.
So this kind of overlap, we didn't calculate the semantic overlap. We only like calculated the word level, token level overlap.
Okay.
Yeah.
Okay. All right.
Yeah. So I think there must be a lot of open questions related to this data set, because our analysis is like this. We only calculate the shallow patterns, but we didn't do, for example, contrastive cases to really understand whether the model really made use of these patterns or not. Yeah.
Can I ask a question?
Yeah.
Could you show the results of BART and the GPT-2?
Oh, yes, this part.
So from the result, is BART is better, right?
Yes.
Why BART is better than GPT-2? Because I think GPT-2 use a much larger training corpus.
I think this question is very empirical. I don't have a very intuitive answer to certainly answer this question. But for some of the problems, because we also do other generation tasks, I think for some of the generation tasks, BART performs very well. So one very salient example is abstractive summarization on the CNN Daily Mail dataset. So, but for other datasets, well, I believe the answer is empirical. Sometimes this model performs better, sometimes the other model performs better. And it's not necessarily for every data set, a larger model with more training data performs better. This is our understanding.
Okay, thank you.
Yeah, thank you.
Hi, Yue, I have a question here. So what's the generation for human evaluation? But this evaluation result is kind of different from BART, from Blue Score, right?
Right. So human evaluation, we had some like human scoring metrics. I can't immediately tell you the details because I have to take a read again. But basically, I believe the score is from 0 to 3, so the total score.
So according to human evaluation, BART is worse than GPT-2, right?
Right.
This is kind of consistent.
According to the human evaluation, actually, result is the reverse. Yeah, that's right.
Is it?
That's right. So in terms of blue, it's different, right? Yeah.
Yeah, blue is more like this is a blue 4 or blue 1, blue 2.
The blue one. Sorry. No, I have to double check. Sorry, I don't remember. Yeah.
Okay. Okay. Yeah. Sounds good.
I think it's if I'm right, I think it's blue 4. So it's the standard blue.
Okay. Yeah. Blue 4 is probably more useful because it's foreground looks like a more consistent sentences. Yeah.
Yeah. That's right.
Yeah.
I think we use blue. I think mostly we use blue 4. It's not like rouge where it just looks like rouge 1. Yeah.
Okay. Yeah. Good.
Okay. Let me continue. Oh. All right. So I move on to the next task. So this is to put a common sense into a specific task now. So I give you one example on the left where So this is a dialogue between a customer and a restaurant, like the customer service. So basically, the male person said, asked the female person, "Did you enjoy your dinner?" And the female person said, "Oh, I really enjoyed it, and I talked to my family and friends." And Johnny had his own place to play. And when this happens, you will understand who Johnny is. But sometimes it's difficult for like a dialogue system to fully understand it. I think this part of common sense is very important when you try to perform a fluent dialogue. So we collected a data set like this. So data set is collected from English like listening test. So the test consists of dialogues between people in different scenarios. So basically daily life scenarios, looking for jobs, going to school, going to restaurant, etc. So we took the dialogue, we turned the audio into a text, and then we found the correct answer by OCR, and then we did some human reading. So this is again crowdsourcing. So we try to ask human annotators to read the context and break the context in the middle, and then we ask them to find a so basically coin several confusing next utterances, and in order to figure out whether a model can differentiate a correct answer by making use of common sense. So the data set consists of over 8,000 example dialogues, basically the context and the response pairs. And we split them into training, development, and final test dataset. So the common sense knowledge contained in this dataset can be classified into 5 main categories. So the first category is like attitude reasoning. For example, so this dialogue involves 2 participants. So one asks about one states that she's going to take a trip to London to give a concert. And then the other person asks, oh, I'm looking forward to this concert, but can you tell me about your first performance, like singing in public the first time? And then the female said, oh, my legs shook so uncontrollably and I almost fell. So when you read this, so you understand that this is because she was nervous, and you got a clue mostly because her legs shook, and it was also the fact that she sang the first time in public, and the confusing choices contained some other emotions like a disappointment or happy, and there was also a confusing choice that so basically contradicts the fact. The second type of common sense is more like algebraic common sense. So I gave this example earlier. So for example, when you understand that there is a time difference between New York and the local time, then can you calculate the time in one place according to the time in the other place? So the third category is the normal decision making, I would say. So for example, in this dialogue, so the one participant originally did not get the scholarship, and later he received the scholarship in the end. And if this is the case, the normal choice will be to continue going to school. So the choices of the next utterance are designed around this intention. The fourth type is more like a situation reasoning. So in this dialogue, the customer asks about smoking area. And so basically, the smoking table was occupied. And so what would the customer ask next? So when we read this context, we realize this cannot be in a bus because public transportation is normally smoke-free. It cannot be in a hospital either. So the most likely is the dialogue happens in a restaurant, and the next thing to do is to ask for food. There are also like dialogues that contain multiple common sense issues. In this example, the customer visits a museum and the visitor spent $30 on a ticket. And the custodian introduced some exhibitions in the museum and say this statue was purchased by the museum for $2,000, but now it's worth $2 million. So the customer, the visitor said she's glad to spend the ticket money. And so the answer is contains a lot of facts. The correct answer is, oh, the painting worth $2 million is also glad. So basically this is to say, thank you for your visit. We're very glad on your visit. So there are multiple facts in this reasoning part. Beyond these 5 categories, there are also some other categories. For example, when it rains, you should bring your umbrella. So we also included this example. And we put them all into the others category. So this data set is called mutual. And when we finished this data set, we evaluated a few state-of-the-art dialogue systems. And we also evaluated a few pre-trained language models. So so this we perform recall at 1 and recall at 2 and the average recall. The performance of these pre-trained language models are rather below the human performance. The human performance can reach 95 and above, but this model performance are around 70 at the recall at 1. So, but like nowadays, people did more tricks on the data set and they already improved the performance to above 90. So there are some analysis on this data set. We find that algebraic reasoning and situation reasoning are the most challenging for Roberta. And Roberta basically outperforms BERT. We believe that this is because for these 2 types of challenges, the overlap between the dialogue context and the next utterance choices are relatively less, and more calculation are needed, or more external common sense are needed in order to figure out the correct answer. So recent work in our group further showed that this kind of pre-trained language models are really bad in doing math. Okay. So there are some tests to evaluate the quality of the data set. For example, we just did an ablation test to drop some part of the question or some part of the context, and the model performance consistently dropped. So this shows that so the data set do not obviously have a bias that can be easily taken advantage of. So, and also if you look at the influence of the context length, it's not obvious that the model performance drops with the context length. So this shows that common sense knowledge does not quite depend on the number of words in the dialogue. Okay, I finished the second task. Now, yeah. Now let's move on to the third one. The third one is about reasoning.
Can I ask you a question?
Yes, please.
In this case, you are not using any external knowledge base or something like that, right?
No,
just basically use the pre-trained model.
Yes, we completely rely on the pre-trained model.
Okay.
Yeah.
So do you have any estimate if some kind of knowledge base is available, this number can be improved, right? This accuracy type of thing. Is that accuracy?
Yeah. So this is a multiple choice question. So I think the number could be improved. I remember there are some like common sense reading comprehension, common sense QA tasks where they use relevant data set like ConceptNet. They can improve the multiple choice results. But I'm not sure whether if you just use a common sense database such as Atomic or other like common sense databases, you can improve this task directly. This is because the common sense needed are quite widespread. So it really depends on whether your external KB has the correct knowledge and whether the knowledge is so available for the model to retrieve. I think it could be challenging, but potentially it might work.
Okay. All right.
That's just some intuitive thinking.
Okay, thanks.
Okay. So let me move on to this third task. So this is about logical reasoning. And I believe there is some debate on whether logical reasoning is a part of natural language understanding. But my strong intuition is that it's an integral part of our language understanding. Let me give you one example. So suppose that the two of us are walking in the street, and one says, "I feel thirsty," and the other might just naturally say, "Oh, look, there's a supermarket in the corner. Let's go there." But if you try to understand it, there are a lot of things beyond words. So first of all, you need to know that when you're thirsty, you need water. You need liquid. You need a drink to quench your thirst. And the second is you need to know that a supermarket typically sells bottled water. So, and you need some reasoning to connect these two facts together in order to make the correct answer. And I believe that in the early ages of AI, people talk about linguistic reasoning. So for example, sorry if I remember the wrong name of the philosopher. So all humans are mortal, and Aristotle is a human. So Aristotle is mortal. This kind of linguistic reasoning was actually, I believe, was an important topic in early ages of AI. But also, I believe it was because natural language processing was in the infancy age, and people could not really understand the logics, understand language behind languages, and people turned to formal logic in the end. And over a long ages of AI research, so formal logical reasoning has attracted a huge research attention. So nowadays, natural language understanding has improved so much. So I believe maybe we could pick up this linguistic reasoning again. So I'll give you one example here. So this is a this is an English translation of like a public servants test in China. So it's a little bit like GMAT. Actually, we use GMAT questions as well in another data set. And also like, so police exam in the US, I believe. So they all require the testee to have reasoning capability. So in this example, they have a factory and they have workshops and dorms. So, and they say none of the employees who live in dorm A are textile workers. So, and they need another premise to draw a conclusion that some employees working in workshop B do not live in dorm area A. So this is a question that need a multi-step logical reasoning in order to select the correct candidate answer. So again, we made a data set by selecting questions from human exams. So this data set is made in the format of a standard machine reading comprehension data set. So we did compare with existing machine reading comprehension data sets such as SQuAD and DROP and DREAM, etc. So we categorized logical reasoning in this data set into several types. So one type is categorical reasoning. So basically, this is to tell you if something belongs to this category, then it has to follow several characteristics, or it has to have several attributes, and therefore, and then you're given some new instance that follow certain attribute, and you ask what are the correct choices or whether they belong to this this category. So the second type of reasoning, we call it sufficient conditions. So basically, when A happens, B must happen. So this kind of reasoning questions. The third is a necessary condition. It's like only when A happens, B can happen. Or if A doesn't happen, then B doesn't happen. Then A is B's necessary condition. And there are also some questions concerning disjunctive reasoning. So when you have A or B or C, then D will happen. So, you don't require all of them to happen. So conjunctive reasoning is the when you have A and B and C all true, and then D is true. So for this data set, it's a multiple choice question format. And so the random, like a theoretical random guess will achieve 25% accuracy. And we compared several machine reading comprehension models, and we also compared several pre-trained language models. In this case, the pre-trained language model performance is much lower than human performance. So the human performance, we asked a graduate student to take these exams. So basically, they can achieve over 85% accuracy. So if you take the human ceiling, like the best performance of human on the questions, it's above 95%. But for Bert and Roberta, the performance is very close, actually, to the random guess theoretical baseline. And if you look at the reasoning choices, it's more hopeless. So basically, for categorical reasoning, the performance is much better than the other types of reasonings. So we believe that this is because there is a superficial correlation between the correct answer and the question. And so basically the token overlap is relatively larger. But for other reasoning types, the model consistently underperforms the random guess baseline. And I believe that this is because they try to learn some superficial patterns in the training set, which happens not to be the correct superficial pattern in the test set. So the superficial pattern in the training set and test set consistently mismatch, which leads to consistent lower performance even to random guess. So this is again some evaluation on the quality of the data set, and similar to the mutual data set, we find that for this data set, we call it Logica. So the performance doesn't really depend on the input size. So this is an ablation study which shows that if you remove the paragraph, you remove the question, the performance will drop, which means that the data set quality is at certain level.
Sorry, Dr. Zhang, can you go to previous page?
This one?
Yeah. You are saying the length doesn't matter, but it seems like the it's increasing, right?
Okay, yeah, I say the length doesn't matter. Okay, maybe I'm not inexact. I just mean the accuracy doesn't drop consistently as the length goes up. Now, when the length goes up, actually the accuracy goes up. We didn't look at the reason, but if I'm to think about it now, I think it might be because a larger context provides more superficial features for categorical reasoning for this type. But I need to do the specific breakdown analysis to know whether this is true. So again, this is just thinking off the top of my head. I believe that it's again because of superficial features.
Okay.
I think the point I'm trying to make is that this kind of models, this kind of questions, the real challenge doesn't really come from the size, as a lot of other data sets exhibit. So the challenge comes from the underlying logical correlations. Thank you for pointing this out. So if no more questions, I move on to the last data set. So the last data set is the thinking is actually similar. We also wanted to examine logical reasoning, but the data set we mixed two purposes because we found that when we did this project, there was no natural language inference data set that contains a long premise. So this is we wanted to understand when the premise becomes long, evidence integration becomes more challenging, how models perform. So basically, this data set combines a significant proportion of logical reasoning questions and a proportion of long passage reasoning questions. Unfortunately, when we finished the data set, on arXiv, there was one paper with long premise. So this long evidence integration is not our main novelty anymore. But the logical reasoning part is still the novelty. So basically, if you look at the traditional natural language inference scenario, they evaluate some basic linguistic level inference. For example, giving a speech implies speaking, and not sleeping, etc. But for this one, natural language inference is more related to logical inference. The question is that 10 TV programs appeared in September, and so 3 were one type, 2 were other type, 5 were another type. And then in January, only 7 of them were still on show, but 5 of them were still like the sitcom type. So which means the other 2 shows have to be among these 2 shows. So if you realize this fact, so at least one of the shows that were canceled must be a long drama, and the contradicting hypothesis is that no hour-long drama remain in the air, etc. So you really have to figure out the underlying logical correlation between the facts in order to make the correct choice. So so this is a reading. So the natural language inference dataset comparison. So so our dataset is unique in several aspects. For example, it contains a lot of different logical reasoning types, and it contains long premise. The dataset statistics is shown here. So this dataset is taken from a lot of different exams, including the police recruitment test in the US and the GMAT, etc. So those we just crawl the information that are publicly available online. So we also categorize the reasoning types in this dataset. So for example, we had co-referential reasoning. So this is similar to some multi-hop reasoning reading comprehension data sets. You need to understand co-references in order to make evidence integration. And we had a large proportion, over 40% of the data set involves formal logical reasoning. So in this aspect, the challenge are the same as the Logica dataset. There are also some numerical reasoning part, like temporal reasoning. So this is complex. I would choose not to go into the details for time reasons. And there was also like multiple evidence integration. This is deeper than mere co-referential reasoning. Okay, so this last example contains temporal reasoning, information integration, and analytical reasoning. So okay, so let me skip to the results. So I just wanted to show that for this data set, the human performance is still quite high, but the pre-trained language models get F1 scores that are around 50%. So they lag much behind human performance. And if you compare with other natural language inference data sets, so the state-of-the-art models already reach or surpass human performance on many of these natural language inference data sets. But for this control data set, there is still much gap. So logical reasoning is still the most challenging part. We find that similar to like Winograd scheme challenge, so pre-trained language models perform quite well on coreferential reasoning. And for these long analytical reasoning questions, because I believe there are superficial patterns to make use of, this model can perform quite well. But when we go to logical reasoning, the challenge is similar to what we observe in logica. Ablation study I skip, so conclusions are similar. I have to also skip these case studies. So these studies definitely review the fact that Roberta makes use of very superficial patterns like word co-occurrences for answering the questions. All right, so let me quickly draw the conclusion. So in this talk, I shared with you some of the work to probe into the bottlenecks of current NLP. And so overall, I believe that these high numbers in each of the benchmarks are a little bit overstated. It's because we are like learning to take exams. So after we pre-train a model, so we ask the model to overfit a specific benchmark, the probability distribution of a specific benchmark. And then we claim that natural language processing models can do well in this particular task. But in fact, this is not true, because even for one task, there might be different domains, there might be different benchmarks that highlights different probability distributions. No model can solve all these tasks very well. So it means that natural language processing are still quite fragile. And even if you train a model that suits a particular benchmark very well, the model are easily hacked by changing the input slightly, even when the meaning doesn't change. The model can perform much worse according to these hacks. And we try to probe into the reason from different perspectives. So, so in this talk, I shared with you some work on probing into whether the problem comes from common sense knowledge or does it come from logical reasoning. And the obvious conclusion is that logical reasoning is an issue. But logical reasoning is what we do in human learning. It's not what we do in machine learning right now. We also found some other fragility issues, like for composition, exponential composition, for mathematical questions. So basically everything that involves a little bit of reasoning to figure out this kind of pre-trained models becomes fragile. So we believe that what they do is to remember superficial patterns. And we also found that even when we evaluate its capability of memoization, it's still very weak. So when we specifically design data sets to test the memorization skill of these language models. So the conclusion is there's still a long way to go. And it seems to me that we definitely need to integrate logical reasoning capabilities into natural language models, or like Bing's work, like continual learning. We definitely need to include some like continual learning capabilities, reasoning capabilities to make natural language processing really robust, and we would then make it more commercializable. Thank you very much.
Thank you, Professor.